Shankar, and I'm the director of the Energy Systems Engineering program here at Lehigh University. This is part of our ESE seminar series. Offer, we present talks on various subjects, and the, um, the theme for this semester is the energy transition. That is, the electric grid is essentially changing from what it was, a traditional grid, to one that can accommodate renewable resources in an effort where we decarbonize the grid by a certain time horizon. That time horizon varies from one country to another, but the writing is on the wall. As and in many ways, we are somewhat behind the eight ball. The first lecture that we had in this series basically gave a landscape of what is happening during the transition period, what some of the metrics are, and how well we were doing. And so, what we will dive into for the remainder of the seminar series is looking at some of the tactical methods that are being utilized to address some of these problems. And the talk that you hear today is about resource adequacy. Resource adequacy and grid reliability are those wonky things that must be met according to regulators. And resource adequacy simply means, do you have the resources to meet peak demand at all times? And uh, most regulators have very strict guidelines. A guideline that is accepted is no more than 24 hours of outage over a 10-year span. 10-year span. So if you do the math, it's 24 divided by 87,001. And so it means it has to always meet demand, even during, especially during peak demand, always, and very rarely should it fail. So this takes on a whole new color when you add renewable resources. And that's why we've invited Frank Felder, who's an expert in this area. He'll be talking about how modeling and policy needs to transition as we go towards a net zero power system. Frank is a principal independent electricity consultant, a senior fellow at the Oxford Institute for Energy Studies, and a visiting researcher at CAPSARC, an international energy think tank. He was with the Rutgers Energy Institute, research professor and Center for Energy, Economic and Environmental Policy at the Blaustein School of Planning and Public Policy. He actively teaches and researches electricity markets and the reliability and resiliency of power systems. He holds a doctorate in technology management and policy from MIT. So before I hand it over to Frank, I just want to give you the house rules. Frank will talk for roughly 1 hour, and then we'll entertain questions for the remaining 30 minutes or so, with preference given to students with the first questions and then to the general audience. Okay, Frank, it's yours.
Great. Well, just want to make sure you can hear me, Rudy.
Yes, I can hear you.
Great.
And we can see your slides too.
Great, thank you. So thank you, Rudy and Susan, and the program, Masters of Energy System Engineering. So as Rudy gave a great introduction, this is a good example, not the only example, of linking technical engineering with, I'll say, economics, technical economics, and public policy. And kind of beneath the surface today is the theme that those need to align, the physics, the engineering, the economics, the public policy, and then the political acceptability or political process. All those need to align, and this is one example. There are many others in the energy transition of this. So what I'm going to do today is just first motivate the subject. It's been in the news in the last several years, and even in the last several months, where we've had large-scale major blackouts in Texas, for example, a lot of close calls. Depending on one's point of view, people pick different attributes or causes of these or contributing factors. So one is the transition to renewables, another is the changing climate, the non-stationarity of the climate, giving us severe weather, such as a severe heat wave or winter storms, that then ripple through and lead to these major blackouts. Other factors you'll see in a moment, but it's hard to, I would say pick up a paper, but open, I guess, your web browser and not hear about this issue, not only in the United States, but internationally. And so the question is, what do we do about it? What's the problem? How do we analyze the problem? What do we do about it? What can be done about it? And so forth. And so resource adequacy is one methodology that gets at this issue, and more about that as I go. So why is it in the news? Well, one is the substantial increase to intermittent and variable renewables, wind and solar PV. In the United States and elsewhere, a lot of planned retirements of coal plants and some nuclear, depending on the country. Coal plants because of their contribution to air emissions, both CO2, greenhouse gas, and other air emissions, aging nuclear plants, aging coal plants. In the US, the US Environmental Protection Agency is working through a series of rules, again, directed at reducing greenhouse gases. Growth in electricity demand, this issue has really taken off, at least in the US in the last year or so. Data centers are the highlight, but also electrification of heat and industrial processes. Those are longer range issues, but again, they're motivated due to climate change concerns, electrifying the transportation sector, industrial processes, residential heat, for example. Long generation interconnection queues. So in the US and elsewhere, but particularly the US, getting new projects, solar and wind in particular, connected to the system in a way that ensures reliability and the ability of those power plants or wind farms, power generation facilities to inject power into the grid and get it to where it's needed, requires a series of studies, and you have these queues or lines to interconnect, and you have hundreds of thousands of megawatts, gigawatt levels of projects in development waiting in these queues. Not all will materialize. And then combine that with a demand growth and retirements, you start getting this notion is, are we going to run out? Are we going to be resource inadequate, not have enough resources to meet demand? In the US, but elsewhere, issues with limitations on interregional, also intra-regional, but particularly interregional transmission. Transmission is one way to help address supply and demand deficiencies because you can move power great distances, you can leverage different time zones, you can leverage north-south, so different weather conditions and so forth. And as I mentioned in the prior slide, these recent blackouts in Texas, California, and some close calls elsewhere. So what I'm going to do today is spend maybe 20 minutes or so on the fundamentals of resource adequacy. Just what is it? How do we think about it? How do the engineers model it? Where does the economics get involved in this? And how it's manifested in the US in terms of policies that Rudy mentioned. And then the last 40 minutes or so, I'm going to make the case for how to improve not just resource adequacy analysis, but reliability analysis in the context of the energy transition. So I'll kind of sketch out a framework that I think will not only improve the thinking, but also the outcomes during this transition. Okay, so let's just start with what a generation unit is. Typically with generation units, nuclear, coal, natural gas, wind, solar, hydro, whatever, what we want is energy, megawatt hours, or at the retail side, kilowatt hours. And how do we get those megawatt hours? Well, we convert capacity, megawatts, into megawatt hours. And that assumes that the unit is available. It physically can be operated, turned on and operated and ramped up and ramp down to produce the megawatt hours that the system operator or the system needs. So what's important is different units have different capacity factors, both based on their underlying technology, but also their economics. So for example, wind and solar, their capacity factors are limited by the availability of wind and solar. Nuclear is a baseload unit, so if it's well operated and maintained, it will run 92% of the time in the US. But nonetheless, it may fail for a variety of reasons, refueling, just a planned outage, or just it fails for whatever reason, a major component breaks, requiring the shutdown of the plant. So these capacity factors are important because they affect the comparison, both in terms of the energy value, how much energy, megawatt hours, a generation technology can produce in a year or in the summer, but also their availability, their resource adequacy. Are they available when the system needs them? So you can have a combustion turbine whose capacity factor runs 5% of the time a year or 1%, but it still could have a high reliability or resource adequacy value because when called upon, it's almost always available. So even though it's only infrequently called upon, the fact that it's called upon and can produce and is flexible and has other attributes is important. And so these overall metrics of capacity factor and energy production, need more detailed description of how they fit into modeling the resource adequacy and the reliability of a power system. So the North American Electric Reliability Council, NERC, so it's North America, has reams of reliability requirements and criterias and guidelines and best practices and so forth. But if you had to kind of boil it down to two elements, and Rudy mentioned one of these, is the bulk power system. So that means generation and transmission. So to the engineers, bulk is referring to generation and transmission, should be planned and operated to avoid widespread cascading interruption. So widespread cascading interruption is the NERC's word for blackout, a rolling blackout, an uncontrolled blackout. So that should be avoided, right? So that is not acceptable. The bulk electric system must also demonstrate the ability to withstand more severe contingencies. So, when you have the 1 in 500-year ice storm, the system is not built to prevent any blackouts or any loss of load during that time period, but it should stay cohesive. It should be kind of maintain its engineering integrity so it can recover to serve load. And then the element that Rudy mentioned is the frequency of having to disconnect firm load. So firm load means customers who are willing to pay for electricity. They're willing to pay whatever the rate is, or in a market, whatever the market price is, should not exceed one time in 10 years. And that one time in 10 years is interpreted differently in different regions of the US and the world. Sometimes it's interpreted, as Rudy mentioned, 24 hours in 10 years, so that would be 2.4 hours per year. Sometimes it's just interpreted as an event, one event where demand exceeds supply. Now, what does it mean when demand exceeds supply? There's several measures system operators take before disconnecting firm load. They may operate generation and transmission at emergency ratings to avoid disconnecting firm load. They may reduce their operating reserve requirements. They may reduce voltage, so a brownout, so to speak. So depending on the part of the world or the region in the US, the one time in 10 years and what it means to quote an event, is it literally disconnecting firm load or starting one of these more emergency procedures I just identified? For example, reducing voltage. Does that count as the event? Well, that depends on the region and the interpretation and the practices. So at a high level, if you put reliability, and this is true, I would say worldwide or almost globally, reliability is the top box here. And then underneath it, NERC would break it apart into two components, same elsewhere in Europe, for example, into resource adequacy, which is what we'll talk about, and security. Security here means the ability of the power system to withstand a failure, such as a large generation unit or transmission unit tripping offline. Not physical security as in, people, intentionally breaking equipment. And so that's frequently labeled N-1, N being the total number of system components, generation and transmission. So N-1 means if one major component fails, the system to the user, you and I, at our houses or work or school would still have electricity. So the analog would be if a 4-engine aircraft was flying and it loses one engine due to whatever, the rest of the plane can maintain its altitude and its speed with the remaining 3 engines. In other words, it can withstand the casualty, the breakdown of one of the engines. Now, presumably then the pilot would adjust the altitude and the speed of the plane, given now that she only has 3 engines to work with, and put herself in an operating envelope such that if the second engine broke, she could fly the plane on the remaining 2. So resource adequacy is, do we have enough supply? And that can be delivered at the bulk power system. So we're talking generation and transmission to the distribution systems. So typically it's broken down in terms of the engineering literature into generation adequacy, generation and transmission adequacy, and then not surprisingly, all 3, generation, transmission, and distribution adequacy. Most of the focus is really on generation adequacy for 2 reasons. One is generally the transmission system components are a lot more reliable than generation components. A transmission line just doesn't have the moving parts that a nuclear power plant has, for example, and its availability, the probability of its being available when you need it, working is probably 0.99, basically failure rate on the order of 1%. Whereas a generation unit, its failure rates are on the order of 10%, 5%. So about an order of magnitude or half order of magnitude difference, speaking loosely. And so we focus in on generation adequacy because the failure rates are higher, and that's where the problem is. The second is just model tractability. The math, these notions of resource adequacy came out, when computers were just starting, and the computations were done by human beings and not by mechanical devices. And so for tractability, people focused on problems that could be solved using the limited computational capabilities that we had at the time. And so there was a harsh trade-off between what we can solve numerically and quickly and the system. So the focus was on the generation piece. So Rudy laid it out. Historically, before the introduction of renewables, solar and wind, really, the power system was dominated by thermal power plants, boiling water somehow, oil, gas, nuclear, even biomass, or hydroelectric facilities, again, depending on the region. And all those units were controllable. And certainly the thermal units, what really limited their ability to produce is if unforced outage, they just broke, or if they were on planned maintenance. For hydro resources, again, depending on the region and the resource, it could be energy limited. Hydro resources have high availabilities if they have water, when they have water, but if, during off seasons or droughts, the facility itself could operate, but there's not water to go through the turbine. But their availability of the turbines are very high in general. So what was really limiting for a thermal system wasn't the fuel. You could store the coal by the power plant. Nuclear, you would have 18 months, 12 to 24 months of uranium in the core at the time of operations. Natural gas, you could store it, expensive, but you had a pipeline system that can move it thousands of miles when you need it. And so it was less of a concern. So you had the system where the focus was on the random failure of generation units, thermal generation units. For the most part, there were enough thermal units that were rampable. They could go up and down. You had enough combined cycle coal, flexible gas turbines that could quickly come online if necessary, ramp up and ramp down to match supply and demand. And so the key question was, do you have enough extra generation, a capacity margin or a reserve margin, to meet whatever resource adequacy requirement that the regulators had adopted? So in the US, that would be the one time in 10 years. And so there are two metrics. They measure the same thing. The only difference is the denominator. Sometimes people use these terms interchangeably. So it's just important when you're doing the detailed studies to really, make sure you're using the same definition, because by changing the denominator, you change the actual percentage and you would get the wrong impression. So the capacity margin is total generation capacity, just nameplate or maybe adjusted by season minus peak load divided by the generation capacity. In a well-run system, the amount of generation capacity, total generation capacity, exceeds peak load. It's an inventory problem, and it exceeds on a large thermal system roughly 15 to 18%. Reserve margin, same numerator, but you divide by a smaller number, peak load, smaller than total generation. And so the reserve margin would give you a higher percentage. So it's important. Typically, it's capacity margin that people are talking about, but just as it's not a small detail, but you got to get the nomenclature right, because you could inadvertently misrepresent the level of excess capacity on the system. Okay. So how did we do resource adequacy? Well, it's an inventory problem, no different than shoes in a shoe store, except all the electrons are the same, but presumably you would, don't want to run out of shoes more than one time per week or one time per month, depending on your business model, the cost of inventory shoes and your customer base. But resource adequacy is, do we have enough generation so that when we account for random outages and planned maintenance, we have enough supply to meet demand, except for one event in 10 years or 24 hours in 10 years. Or in Europe, they now translate it to expected unserved energy, 3 hours per year on average. So you have to define resource adequacy. So that's why I belabored the capacity and reserve margin definitions. You have to have some set of metric. Typically in the US, the metric historically has been this loss of load probability or loss of load expectation, although the metrics are moving towards other metrics. You have to have a method and a model, and these models are assumption dependent. Small changes in assumptions, as you'll see, can really affect the outcome, the calculation, the metric that the model reports, and therefore whether or not the system is compliant. You need data about the physical availability of generation units. Are they less available during winter? What are their maintenance requirements? And so forth, any D rates in them. And so you need a lot of good data, and NERC and others collect that data. And then you need some type of policy to build the right amount and types, so you have enough overall capacity, and it's the right combination of capacity for both economics and environmental reasons. And how do you do that? In the old world, before, quote, deregulation, that was done through the utilities planning process. In the new world, and the world like Europe and much of the US, where we have capacity markets, that's done through a capacity market mechanism. So we'll talk about how that mechanism works. So you need this combination of engineering. How do I define reliability? How do I calculate it? What are the methodologies? Is it based on good data? And then, given the results of that, I need a policy, such as a resource adequacy policy, and a mechanism. What's the policy mechanism? Integrated utilities or electricity, wholesale electricity market, and then an outcome to ensure that those resource adequacy requirements are being met. So the definition here is resource adequacy is to ensure there's enough energy so we can convert capacity into energy to meet demand over a given period of time. Historically, it's been peak hours, because if you can meet the peak hour requirement, then you can meet the off-peak requirement, which could be 60% of the peak requirement for any given time period. But now with solar and wind, and you'll see in the interactions, but you can imagine maybe the peak hour is not the hour that is the most threatened or has the it was most likely to be resource inadequate. It could be other hours in the day, such as the 5 p.m. when it starts getting dark, solar is not producing. Maybe the peak hour was at 2 p.m. in terms of overall load, but at 5 p.m. without solar, or a much reduced amount of solar, maybe that's the hour that becomes the concern. And so that's where we'll start talking about the energy transition. So now there are multiple models. There's probably 5 or 6 or 7 that are widely known. Some are open source, some are proprietary models. One is GE MARS, the multi-area reliability simulation model. This just summarizes, a little bit more detail. You have the performance data, you have supply assumptions, outage data, you put in a demand forecast, you run a model, and you calculate using a Monte Carlo methods what's the probability of having more demand than supply. You then figure out, is that sufficient or not? If not, what needs to be the planning reserve requirement so that you meet the adequacy requirement? And then you figure out if you're surplus or short supply. I won't belabor this, but just for your information, I just wanted to provide some GE MARS. NREL, the National Renewable Energy Lab in Colorado, has its open source model. I think it's Julia. There's other models by other consulting firms. And the purpose of this slide is just to let you know that these requirements and interpretations vary. What seem are slight, word changes, don't seem that important, but small changes in words affect the criteria and affect whether or not a system meets that requirement. So these models and definitions are quite sensitive to input assumptions and definitions. So how does resource adequacy work at a high level? So in this simple system, there are 3 generation units, striped, solid, and checkered. You run a Monte Carlo, so you flip 3 coins, penny, nickel, dimes. Probability of a head is 0.95. Probability of a tails is 0.05. If you get 3 heads, all 3 units are available. 2 of the 3 heads, only 2 of the units are available. You do this thousands of times, and you create basically an available supply probability distribution curve. You overlay it with your load distribution curve, and where there's more load demand than supply, that's your loss of load probability, loss of load expectation, the amount of unserved energy over a year. So you would run these Monte Carlo simulations, 1,000 simulated years for the year 2030, let's say. 10,000, there would be some convergence criteria that you would meet, and then out pops these metrics, these loss of load expectations, the amount of unserved energy, and so forth. And then the engineers would look at that. Do we meet NERC requirements? And if not, what needs to be done if we have a capacity market so that we, in 2030, we have enough capacity, or if we're an integrated utility, what additional generation, transmission, demand response is needed. Now, the world gets more complicated with renewables because their production is time dependent. For thermal units, for the most part, you could say their ability to produce was not time dependent. In the summer, they could produce less than in the winter just due to the rating of the machine, but you would account for that. But with solar and wind, what's important is not only when they produce relative to demand, but when you add in energy storage, which you would store during surplus and then produce when there's shortages. So for example, when there's still relatively high amounts of demand on the system, but solar in this example starts decaying away because of nighttime. So now the chronological element of the system, hour 1 to hour 2 is now connected. So these resource adequacy models to account for renewables like wind and solar and energy storage, need to account for the fact that what I can do at this hour depends on what happened last hour and the previous hour, because those hours affected how much energy I injected or withdrew from storage, right? So these chronological models become critical. In fact, that's now the practice. So maybe 20 years ago, you wouldn't necessarily have to set up these resource adequacy models as a chronological model. You could just randomly sample just peak hours or every peak hour in the day, or just randomly sample hours in the year and not worry about the chronological piece, because that was really a second or third order issue. That is no longer the case. So here just summarizes three of the major metrics that are used. They have slightly different definitions, just need to be precise with them. And there are other metrics that are now being introduced, particularly those that account for risk. So some type of metric on variance. You limit the second or third standard deviation to be smaller than some amount, or conditional VAR or VARs. So what's one major metric? Oh, well, so that's on the engineering side. Do we have enough supply to meet demand? How big is the problem? How do we measure it? Do we worry about tail risk as well? So then the question is, well, what's the cost of not serving demand, right? So we disconnect demand, or we put the system in a higher probability of having a rolling blackout by reducing the operating reserve margins. So the value of lost load is a generic number that planners use to trade off, should we invest in more capital, generation capital, to reduce the probability. So as you add more generation capacity, the system becomes more resource adequate. It reduces the probability of having to disconnect firm load for not having enough supply, but you pay a cost. You either pay the cost of the capital, primarily the capital and fixed O&M of the unit, versus the economic and social cost of not having enough generation, turning off lights at your home or a hospital, or shutting down a government building or industry. So that's what the value of lost load is getting at. I'll just talk about briefly three interpretations. One is it's a literal number. It's an estimate, there's some uncertainty, but that is a number. And maybe it varies by customer class and season and so forth, but it's a good number. It's something that the number physically represents the lost economic output or social costs in dollars of not having electricity. Another version of it is it's just it's one number that's really trying to represent a demand curve, and people have a graduation level, a decreasing demand. You're willing to buy more and more power as long as the price keeps going down. And the third is it's just a planning tool. You need a number to conduct these trade-offs that I just mentioned. And the idea is not to have a perfect number, but just a number that's acceptable, that reflects that not having electricity is costly to society. And as long as we're somewhat accurate, order of magnitude, half an order of magnitude, for the purposes of planning studies, that's good enough. Now, in the US, the way to address the policy, do we have enough resources to meet demand, are capacity markets in regions of the country where we have organized wholesale electricity markets, those ISOs, RTO markets. But other parts of the world do other approaches. I wouldn't say ERCOT's another part of the world, but another part of the United States is they've been looking at strategic reserves. Do we just have an inventory of power plants that are only set up to run during emergency? So anyway, there's a wide range of policies that can be directed at trying to ensure there's enough generation capacity to meet demand. And so the purpose of this slide is just to let you know that even though I may default into talking about capacity markets, there are many different mechanisms that are organized via volume-based, quantity-based, or price-based. Are they market-based or non-market-based? So there's different ways to address the problem. Okay, so I spent a little bit more time than I thought I would on outlining the fundamentals of resource adequacy, but hopefully that will set up kind of what are its limitations, where's the thinking going, and where, in my view, the thinking should continue to go. So we'll switch gears to a more of a normative analysis or normative argument about how do we improve not just resource adequacy, but reliability analysis as well. So I think there are two public policy questions or two major public policy questions. One is, what are the cost-effective measures to reduce the cost of power outages, right? So you can imagine a policy, a politician, okay, reliability is really important. Whatever reliability we want the electric power system to obtain, we want to do it in the most cost-effective way. And presumably that involves a combination of generation, transmission, distribution, and load management. And if I have a dollar, that next dollar that I'm going to spend on reliability of the power system, I want to put that dollar or proportion that dollar across those four major categories, generation, transmission, distribution, and load management in the most cost-effective way. So Frank's been talking, I've been talking about generation resource adequacy, but maybe the next dollar, the incremental dollar, the marginal dollar should be spent on improving the distribution system. Most outages that you and I experience are due to the distribution system failure, typically minor and very localized, not a major storm that happens every 10, 20 years, although those are more severe. So one question is, what's the most cost-effective combination of measures to reduce the cost of power outages? And here I mean not just economic cost, foregone production of a semiconductor chip, but social cost, the fact that someone can't get access to a dialysis machine and that has substantial serious health consequences. That is a real cost, hard to measure, but we know it's high. And I want to include that when I talk about cost. So it's not just economic, but also social costs. And then the second question is, okay, now we have this dollar to spend and we're going to allocate X percent to distribution, Y percent to generation resource adequacy. What's the most efficient policies to do that? On the distribution side, is that adding transformer banks, or is that installing batteries as a backup at a major facility? On the resource adequacy, is that mandates to weatherize the power system for very extreme weather, cold or hot weather? Or is it to increase the reserve margin? Or is it to tighten down the penalties, increase the penalties for not being adequate, not being able to provide energy when committed to in the capacity market? So there's two sets of questions. Where do we spend the next dollar, and what's the set of policies, market regulation, mandates, information to get the outcomes we want? So I'm going to make four major claims. One is social and economic costs should be explicitly included in resource adequacy analysis. And the argument here is you're doing it implicitly. There's no way around getting the fact that any analysis, any set of criteria is implicitly making a statement about what they value reliability at. And so by making it explicit, you improve our thinking, improve the consistency, improve the policies. So there's no way around it. So either you do it implicitly or explicitly. I would argue we should do it explicitly. Secondly, resource adequacy is evolving towards a more probability, reliability, resilience, and adaptability. I'll talk about that more as we go. It's starting to account for a broader set of failure initiating events that result in blackouts. And I think it can go even further. Now, in order to do so, these broader analyses, broader than just resource adequacy analysis, but include reliability, so the N-1 piece as well, and resiliency or adaptability, the ability of the system to correct itself and the ability of customers to mitigate the cost of power outages. It's just more computationally expensive. The good news is, storage of bytes and bits is decreasing and the speed is increasing. And so there are ways to handle that. And then I would argue or claim that these analyses, although more complicated, not just computationally, but also data, can help inform policymakers even given the current structure where we separate resource adequacy from security, N-1, N-2, analytically, we treat those differently. But even if we, down the road, if we integrate those into criteria that are more comprehensive and system-wide. So a major component of existing resource adequacy is they are centered around what's called independent failures. So the fact that if a generation unit 1 fails in my Monte Carlo simulation, the probability that generation unit 2 fails does not change. So the conditional probability of knowing that generation unit 1 has failed does not change the probability that generation 2 unit will fail. Now that independent assumption was done, not surprisingly, back in the 40s and 50s due to tractability. It's just we didn't have the computational time or resources to account for the much harder problem of dependent failures. So we assumed all the generation units were these independent coins, and we're just flipping independent coin tosses of weighted coins. But we've learned, although to be honest, I think in both the academic and research literature, this was clear for 60 years of, or 50 years at least, that it's the dependent failures that are less frequent than the independent failures. So think of a severe weather or hurricane or cybersecurity, even a physical security or maintenance practice that trips multiple units, so forth, that they're less frequent, but they're more severe. They're more severe because at a single moment or in a close period of time, 5, 10, 20 minutes, an hour, half a day, you lose multiple units. So think of a severe storm or icing that freezes up key components in power in 5 or 6 or 7 or 8 power plants of various types, wind turbines, nuclear, natural gas, as we saw in Texas, and they fail right away or within a 6-hour period. So that probability is less frequent, 1 in 20 years, 1 in 10 years, whatever the weather data tells us, but it's more severe. And so you then have its contribution can be magnified when it does occur in terms of the resource adequacy. Now, these dependent failures, at least in much of the talk now, have focused around severe weather, this top box. But if you go through the data, historical data, you see that there are many other sources of these dependent failures. So I'll leave it to you to look at those. We should include cost for both the social and economic costs. So typically, not always, the value of lost load is some estimate of, the industrial cost or economic inconvenience. But we should include healthcare, physical security if stoplights aren't working, or the police and fire departments, have less visibility into what's going on because they don't have electricity to respond to emergencies. Now that requires monetizing those costs, which is difficult, but better to be explicit about that and to recognize the high costs and try to account for the uncertainties than just to ignore them. And so I would argue that one can do that through a variety of techniques. I would like to then broaden resource adequacy and reliability to a broader set of definitions. So up top here, typically reliability was broken down into resource adequacy and security, sometimes called operational reliability. So these terms mean different. In Europe, they'll refer to energy security, sometimes as resource adequacy, but sometimes that term is used for N-1. So you just got to be careful with the terms. And then expand it to include resiliency, which is the ability. So typically resiliency has 2 components. One is ability to withstand something like a severe weather. And then secondly, the definition of resiliency, the ability to bounce back. And so in this diagram here is how quickly can the power system return to its normal operation, how quickly does it bounce back, particularly after a severe event like severe weather. And so my argument here is we need to include both reliability, the resource adequacy component, the security component, and the broader resiliency component, how quickly we can restore the system if we're going to be cost effective in setting up our policies. The point of this slide is just to show that people do make these estimates for the social and economic costs. I'll acknowledge they have wide uncertainties about them just due to the methods. But the point is they're very important, that, not having electricity, a widespread blackout of either rolling or uncontrolled is costly, both in economic and social terms. One way to get at the social cost is the impact on lives, on health outcomes, physical security outcomes. So we saw in Texas, I believe about 100 lives were lost as a result of the lack of electricity, either directly given the electric heat use in Texas, or someone taking an action such as, sleeping in their car and then freezing to death, unfortunately, because their house didn't have electricity. So we do this in other parts of energy policy, climate policy, environmental, workplace policy. We put a value on a statistical life. We're not saying that's the value of an actual human life, but just for planning and optimization purposes, so that we can best use resources to prevent and save other lives and reduce adverse health outcomes. So then this leads us the ability to put this in an optimization framework where we're trading off investments in resource adequacy, or N-1, to go from N-1 to N-2. That's costly. To be able to have more work crew and spare parts to restore, to increase the resiliency of a power system. That's costly. We have spare parts sitting in a warehouse that are used once every 20 years. And work crews that are, extra work crews that, are only deployed in rare events. Those are all real costs, and they're worth paying so that we avoid greater costs on the social and economic. And so we're faced with an optimization problem. Now, to pretend otherwise, that we're not trading off real costs, both in terms of the cost of the outage and the cost of preventing and reducing the outage and mitigating the consequences of an outage. So, for example, a grocery store having backup generation to protect its frozen food during an outage, an example of adaptability, it just means we'll solve the problem incorrectly. So it's difficult to quantify these costs and to put them into an optimization problem. But I think that, that's where we can get to, and by doing so, I think it can improve public policy. So there's work over time. This is by no means a short list of references in terms of the amount of types of dependent failures. They're high consequences. They've been well documented over many years. My favorite example is this paper headline in the New York Times in 1939. Now, if you read the headline, so storm hits east, darkening city. And they talk about this virtual blackout. This is 1939, so at the start of World War II. So why are they using the term virtual blackout? Well, coming out of World War I and World War II, both in the US and Europe, cities would intentionally black out. Think about the iconic bombing raids of London, and you had the blackout police, guardian or patrol, and the black curtains you'll see in the movies in the 1940s. And, so a city would intentionally black itself out in order to avoid enemy bombers being able to identify targets. So that was the blackout. So blackout was something that was done intentionally and in a controlled way as a positive response to a dreadful situation, which was, a widespread war and bombings. So they had to use this term virtual because we're building out the power system. And now we have a blackout that's unintended, that's completely negative, which is, the system just fails due to some reason. And here it's due to a storm. Not surprisingly, in the 1940s, a storm comes through, power lines fall. We're just learning about the interaction between how reliable power lines and generation units are. And so this notion of, severe weather affecting power systems and other engineering systems, agricultural for 5,000 years or so, is well known to us. It's only somewhat lately that we're really trying to more formally include this in our analyses. So my next claim is that we should accelerate the current ongoing process of introducing or expanding resource adequacy to include other sets of dependent failures. And what the current many folks are doing at NREL and EPRI and elsewhere is including severe weather or just weather, because they want to get the correlation between wind and solar, right? Because that's important, as we saw in that diagram maybe 8-10 slides ago, where we had the chronological ordering of hours, and we had solar coming on and going down, wind varying with the time of day, storage is charging and discharging, load is changing due to the business day, and so forth. And so by really understanding that correlation and the variance around those correlations between solar and wind, that affects how much storage you put in, that affects the calculation of how valuable of adding another solar panel is. If the hour that you have the highest inadequacy that you're concerned with is a nighttime hour, adding more solar in and of itself may not provide electricity when it's needed unless you also add in storage. So the marginal contribution of solar and wind and storage are now interrelated and depend on the weather profiles, the correlation between wind and solar. And same going with transmission. If you interconnect a broader region or firm up the interconnection across larger regions, then the wind variability reduces, and that then affects resource adequacy. And so much of the current effort has been focused around climate and weather and renewables and updating resource adequacy models to account for these dependent, they call them correlated failures. Well, once we've taken that step, I would argue, let's take the other steps regarding severe weather, ice storms, hurricanes, heat waves, cybersecurity, maintenance practices, all the items that I listed that contribute to these dependent and correlated failures. And then once we do that, here's a slide that just exemplified that these metrics can then be adjusted or introduced to account for tail effects. We're not just worried about the average loss of load probability or expectation, but its distribution. So do we have one time in 20 years where we have a major blackout? Okay, so we may want to reduce the consequence of tail events, not along with the average frequency of certain events. I argue here that they can continue to improve over time. We have a conceptual framework where we talk about an initiating event that leads to a power outage, that leads to quantifying it via some type of modeling, Monte Carlo simulation, and then that gives us a distribution of bad outcomes where we can then pull off our metrics of various types. And then the analysis is being done. There are many, many references that are building out this capability. So it can be done. We need more data. The models will inform the data. We get better data, plug it back into the models that will inform what areas where we need to make better models, get better data, which areas are less important. So what's the general approach here? Well, we start out with identifying the type of events that could lead to power outages. We have a historical record, but we can also do it through expertise. So we have a record on weather events, cybersecurity, so forth. We model how those sequences, how come an ice storm of different levels of severity and frequency and timing affect power outages at the distribution, transmission, and generation level. We then make estimates about what those outages look like. Are they days? Are they just hours? Are they localized? Are they global? We then quantify those outages based on the social and economic costs, accounting for their uncertainties. And then we propose new solutions, better distribution systems, backup power, increased resource adequacy, whatever combinations of solutions that address the particular outages, their frequency, their duration, and their costs. And then we repeat the cycle over time in an iterative fashion. As we get better data, we get better on the performance of the systems, of the costs, which policies work, and so forth. And then we can presumably improve the cost effectiveness of achieving our reliability, resiliency goals. This slide just provides a little bit more detail. I won't belabor it. And it just tries to put in pictures the various elements, the initiating events, their categories, how we put that into a model. You can use both top-down and bottom-up approaches, and how we translate those models into outages. We account for resiliency, and then we monetize that. And then that provides the analytical framework where we can then look at various solutions, policy-wide, investment-wise, infrastructure, and feed them back into our analytical process to see if they improve the cost effectiveness. So a major critique, I would say probably maybe the major critique of what I'm proposing is uncertainty. So I get this argument frequently, and it's a valid argument, an important argument, or observation. Look, the uncertainty around economic and social costs is an order of magnitude. And so we're just better setting an engineering requirement. Not perfect, but let's set one time in 10 years. Maybe we need to improve it to account for tail effects. Maybe we should add in an energy requirement. But at the end of the day, we need just a technical requirement that's subjectively informed by economic and social costs. And I would argue, yes, but that means you have set what you value the cost of reliability or the cost of unreliability is. So you've already done it. You've just kind of buried the value that you've placed or values you've placed on resiliency, reliability, long outages, lack of electricity for dialysis, and so forth. So how do we account for that and explicitly account for the uncertainty? And so the way I would argue is, let's see when the uncertainty matters. Where uncertainty doesn't matter, even if there's at a lower bound, you would take the same action as if you took at the upper bound. Then the uncertainty is important, but it didn't affect the decision. And so you can just move on and then focus on those areas where the uncertainty does flip decision, change the decisions. And then that would help articulate what type of data you need to try to reduce that uncertainty. And then at the end of the day, there'll be a policy and political judgment about that. Another question is, are the results of this broader probability, reliability, resiliency, and adaptability? So if you do get this framework up and running, you have all these data inputs, you have this complicated Monte Carlo process, it's appended or attached to an optimization process. There's lots of uncertainty, there's lots of degrees of freedom. You can't model every possible failure outcome. You can only estimate them. If you want to do this in some tractable amount of time, that's useful. How do we know? How do we take a result and say, okay, should we invest billions of dollars based on this result? Well, my argument would be, well, it should give you better results. I mean, if you're careful in the data and the methodology and so forth, if it provides results that are counter to current experience and other models, well, that's useful. You can then investigate which approach does a better job, or maybe both are lacking, but it gives you a point of comparison. If it turns out that it coincides with current practices or thinking, then that's useful, that a different approach, a more comprehensive methodology is reinforcing what you already know, maybe it's providing additional insight. It certainly, I would argue, as I just did, it would help improve on which data, right? Collecting data is expensive and time consuming. Are we better off simulating new weather years under a changing climate, or more accurately pinpointing whether or not a pump storage unit is available 0.89 versus 0.91% of the time, right? So it helps inform where you want to focus in terms of data collection and improving methodologies. And then I would acknowledge that interpreting or presenting uncertainty to policymakers is a challenge. There's no doubt about it. You don't want to say, well, plus or minus an order of magnitude. I think there's a one time in 10 years of a blackout in 2035 or 2030 or next year. It's just that's just hard in a very broad audience. And in some sense, there's a credible concern that you would undercut the legitimacy by reporting error bars or acknowledging the wide uncertainty. That being said, I think people know, policymakers know that there's a lot of uncertainty and there are large error bars. They may not use the terminology of scientists and engineers, but they probably have an intuitive sense that, if we have another major ice storm, things will look a lot worse this winter than if we have a mild winter. And then that is somewhat random. And, there's only so much one can do to prepare. So, I think there's definitely efforts need to be done, but there are ways to try to address that communication problem. So one or two more slides. This table is trying to summarize all the elements so that we increase the number of the types of failure modes that are being used in the models. We consider not just resource adequacy, but also security or operational reliability and resilience, because what we care about is the cost of a power outage. What drives the cost of the power outages is the size, the timing, the durations, and the frequency, right? If we have power outages during mild weather, that's not such a big deal as if we have during a heat wave or a severe winter storm. A longer outage versus a shorter outage, a widespread outage versus a localized outage. We need to include other critical infrastructure, public health, public safety. So it's not just we care about electrons, we care about turning those electrons into healthcare services, police services, housing services, and so forth, economic output as well. And then we need to figure out the cost of adaptability, reliability, and factor in uncertainty. So this slide tries to put in everything in terms of a broad framework. So in summary, we can improve the analysis while we're still using the existing tools. I think just the PRRA framework provides a broader and then a helpful framework, even if you don't quantify things and do the full-fledged modeling, trading off mentally, okay, is this protecting against severe outages or severe weather issue? How big of a deal compared to independent failures of generation units? Which policies are more likely to get the result that we want? A mandate, a regulation, a market incentive, which combination? It frames this explicitly, which is a cost-benefit analysis. I mean, people say we can't put a value on human life, and we do. So we might as well be explicit about it and try to be uniform and consistent across so that we maximize the gains, the reliability, and the benefits of having a reliable power system across everyone. And I think it will help feed into improved data collection and modeling. So with that, I'll stop and turn it over for Q&A. So thank you.
Oh, very good. So could you stop sharing? So maybe,
Yes.
all right. Okay, questions, please unmute yourself, introduce yourself. Open to students first. Introduce yourself, unmute yourself, and ask the question, please. Spencer, you had your hand up, yes.
I'm Spencer. I'm an undergraduate student studying economics and physics. I was wondering if there is a way to model the technology improvement, for example, for batteries, and if that is factored into simulations and analysis.
Yeah, no, hey, Spencer. Yeah, so absolutely. So remember that chart I had, the chronological, you had solar and wind and storage. And so going into that chronological modeling hour after hour, January 1st, midnight, January 1st at 1 a.m., 2 a.m., all the way through the year, are assumptions about the efficiency of a battery. So for example, if the efficiency improves from 15% from 85% to 90%, then the battery can discharge more when it needs to discharge. If it's a flexibility, its ability to charge and discharge, so it has a wider range of charging and discharging, extended life, all that would go in to the modeling, but that's right. So then the question is, if we're modeling in 2035 or 2040 or 2030, what would be the deployed batteries and their efficiency rates and capabilities, the availability of a battery? Does it change when it's extremely cold outside? the probability of the battery being able to charge and discharge under severe weather. So those would be incorporated in the modeling, ideally.
Thank you.
Thank you, Spencer. Thank you, Frank. Questions from students? John?
Hi, how are you? My name is Sajjad Al-Shimmari. I am master degree in ESE. I have a question. What about the new future for the equipment in house or building, like 12 volt and 24 volt, or changing the voltage for the equipment because can be connect to the wind or solar with the less losses?
Yeah, so that's a little bit outside this talk. The challenge is our system has really been built up around, as your question implies, as you know, an AC system. Now we do have large scale DC systems, but now we have wind and solar. They're DC, we convert to AC. And then because, in the US at least, and probably everywhere else, almost everywhere else, 95%, 98% of the system is AC, and you use DC at the transmission scale for large transmission, from Hydro-Quebec to New York, for example, or New England. For solar, if it's distributed, so a question is, I put a solar panel on my house, maybe I should wire my house or have it dual wired for AC and DC. And just when I take the DC power from the solar for my DC load, but then I got to rewire my house, is that expensive or not? Do I have to break into every wall and redo it and so forth? Or is it better just have a converter, at the local? For wind, it's typically located far away. So at some point, you're going to have to inject it on an AC system to get to the rest of the grid, unless you build out the entire grid or almost the entire grid, make it DC dominant. So, I think it's really a cost issue, and I think we're kind of stuck for at least a long time in this AC dominated system. That doesn't mean there aren't special applications, remote applications, or special tailored applications where just a DC system makes sense. Now, some people are just saying build standalone systems. I can think of some that's just standalone, and it's going to be large scale, like NEOM in Saudi Arabia. So maybe a DC design from the ground up makes more sense, given that it wants to be solar and wind dominated with batteries. Maybe you just build a DC, and then when you need AC power for a motor or something, you convert that, like, kind of the flip side of what we do now. It's an interesting question. It's a good question.
Excellent.
Thank you.
I see that Corey has his hand up. Corey, please unmute yourself.
Good afternoon. I am Corey Martin, graduate student in the ESE program. My question is, how do you model for distributed energy resources participating in the transmission energy markets?
Yeah, so that, so first it just makes the problem, the problem is big to begin with, right? If you just, a large power system like PJM, a large wholesale market in the US may have 500 to 1,000 generation units, and then it has hundreds of transmission lines. And so just think of all the combinations of failures and availability. Then the distribution is, 2 to 3 orders of magnitude, right? When you go from megawatt hours to kilowatt hours, you go from, that's 3 orders of magnitude, 1,000, right? So the number of houses and bowling alleys and shopping centers, that are, less than a megawatt, or it just explodes. So there's several ways and that's just beyond our capabilities. If we're not going to model every solar panel in Los Angeles or California. So one is you aggregate behind the meter, you just have a good aggregated model of the distribution system. And then in my modeling framework, depending on the problem you're trying to involve, you then go to a more specific model of the distribution system. You stylize the rest of the system, right? The standard technique, make the less of it the grid, the bulk power system, you reduce its dimensionality. And then if you're a distribution company, you expand your distribution system and, model stylized feeders or different feeders and aggregate it in some way. The Federal Energy Regulatory Commission issued an order recently to try to bring in distributed resources into wholesale electricity markets in the US. And that's a huge problem, just running economic dispatch, let alone the reliability. But I would argue you have to do something to incorporate this, because having a solar panel and a battery at a house, which is common now, 10 years ago, you would just buy the solar panel, but now in California, you're more likely to buy both than just the solar panel. So that should be factored in on how reliable should the rest of the grid be, given that my home, or many homes, but not all, so that's an important piece, and who doesn't have solar panels and backup batteries? Probably economic classes that can't afford them, so they're more vulnerable on other dimensions. They can't go to a hotel or afford to go to a hotel or drive to neighbors because they may not have a car or whatever, or they can't move elderly parent. But nonetheless, we should account for this, right? I mean, because there's no point, if the distribution system becomes more reliable in aggregate, then the value of $1 of the bulk power system is less valuable, right? That's my whole point, and your point. So we should be redirecting that dollar to maybe the distribution system or whatever. And so far that's been ignored, because again, these models coming out of the 50s, there wasn't really distributed generation, or it was a large refinery, so whatever. So they pretty much ignored. In fact, the standards for distribution reliability are just different. They're orthogonal in a sense, or than, SAIDI, KFI, I don't know if you've gone through all those. It's just a different way of thinking about it, and it's one system. And so we got to bring those together.
Thank you very much.
Yeah, I see Spencer has his hand raised.
Yeah, how specific does the location have to be for your simulation for it to be an accurate simulation? Like, does it have to be a specific city, or is it done state by state?
So historically, they've been done at the utility level, and then the utilities may have coordinated. So if there were 3 major utilities in California, they made maybe some assumptions that utility A could get power during a problem from utility B or C, or from a utility outside the state. So typically these analyses were done very aggregated at the utility level. Whether or not the utility, they didn't break it down to cities or distribution feeders or substations within a city. So that was a major disconnect. And given Corey's question, that's a problem, because now, we have the technology, both GIS, load information, computationally, we can run Monte Carlos down to the distribution level and to the feeder level. And that brings in an important piece I didn't really emphasize, was the equity component. I mean, it comes in with the social costs, and trying to capture the fact that households or hospitals or care facilities, dialysis facilities, for example, need electricity. Well, we now can pinpoint, we know where those are. 50 years ago, 30 years ago, you knew where they were, but you had to look at each one up in a phone book. Now, a 13-year-old kid can pull up a list, or, it's, we know where they are and the size and which feeder they're connected to, and we can do an analysis of them. So I think the analysis is moving more towards the distribution, but actual loads, specific loads. And people write these lists. What's the list of critical facilities in the state of California? Hospitals, police stations, fire stations, emergency centers, warming centers, dialysis, pharmaceutical. Can I get my prescription, right? If there's an event and I need to, whatever, my medication.
Yeah, and is all that data publicly available, or is it?
It depends on what it is. Some of it is considered critical infrastructure. So you just can't get the transmission lines and their sizes of, from PJM or from your local utility. There's some type of restriction of getting that data, because it's viewed as sensitive for security, physical security purposes. Some of it is, it's available, but you may have to work to get it. A list of all the pharmacies in Los Angeles, right? Or you could get it maybe costly by Google Maps or some other means. That being said, there are a lot of studies, not just in electricity, but flooding, severe weather outside of electricity, where people are integrating just large data sets of customers, infrastructure, and I think they're just being very creative in a perfectly legitimate way of getting the data set. Some you have to make up or extrapolate, or from housing size, you estimate electricity demand, or you have some distribution of demographics and you impose that to see how many elderly people or people with this heart condition, if you're worried about. I think that's an area where more can be done. I think it could be done in a way to protect any sensitivity, both commercial and security sensitivities, so that researchers, there's a movement I mentioned towards more open source of models and data. I mentioned it with the models, which is, I think, a good thing, because it's a public policy problem. We're spending public dollars, in a sense. You and I are paying for it, and everyone else. So why shouldn't the data be used subject to legitimate concerns to improve outcomes?
Thank you.
Thank you. Questions from the general audience? Questions for Frank? Alberto? Yeah, unmute yourself, Alberto. Good.
Hi, Frank. Thank you so much for the presentation. That was very good. So I appreciate very much what you were talking about, independent events assumptions like IID, and like how we should move away from those. However, and this is actually something that you touch upon. I think that in the industry there is already some familiarity with even Monte Carlo as modeling, which have that underlying assumption. So what do you think is a good way to move into some way of thinking? Because even sometimes the modeling of value at risk or conditional value at risk is also having some IID assumption in there. So like how can we move with planners and with policymakers in order to start passing that information better? Let me make it a two-pronged question. So that would be the first one. And the second one is actually related to something that you just touched upon. When we think about the system operators, whether they are KAIS or PJM or the New York ISO, they rely on vendors in order to do a lot of their dispatch, right? And sometimes these models are quite obscure, right? And they're very customized for the specific need. So even thinking about the open source movement would be great, but seems to me that there is a lot of interest, and in this case it's probably financial, in trying to keep some of these other models still running. And maybe try to patch it, because even for us as researchers, those models are sometimes quite obscure, right? So we know the underlying economics, but try to replicate really what PJM is doing is almost impossible, because it's a very obscure model. So what do you think is going to be happening in terms of that transition to more open models used by directly the system operators that everybody can start looking at?
Yeah, those are, I don't think I have good answers for each. I agree with the first question on the focus on independent failures, the joke of where does the person who lost his keys look for them? Under the light, not in the alley where they lost them. So there's historical, so that's just cultural and educational training of engineers. I mean, when I was being trained to engineer, I took one class. I was required to take one class on probability. I took more, but the typical engineer, I think, of my generation maybe took one, if that. The focus was, 2 years of calculus and ODs and so forth. So part's just educational. There's the more deterministic, and maybe that's just a fact of the undergraduate curriculum. But I think what's really broken out the last 5 years of NERC and other researchers in the industry and the elevation of resource adequacy was just the brute fact that ignoring dependent failures and common cause failures, and there's not even a clear nomenclature in the industry. They use correlated failures, common cause failures, dependent failures. There's argument is which one's a subset of the others. Why the fact that there's just a haze, a fogginess around non-independent failures tells you something about the state. But if you look in the research like Billington, in undergraduate textbooks in the 80s, so he obviously was thinking about it beforehand and teaching beforehand, was talking about, he goes, these deep independent failures don't matter, they're tiny. There's quote after quote and undergraduate second year reliability, not power systems, but just reliability textbooks about the importance of these common cause failures and severe weathers. And so partly it's not to direct it at Lehigh and you, but as an educational, I think it's partly is the models are just unraveling. I think if, you just can't go to a policymaker and they'll ask, well, what about a severe weather event? And you can't say, well, I can, my LOLP doesn't include that. And then I think partly some research community to try to show that the models can be made tractable, that you just don't end up in a blur of uncertainty distributions where you're losing the result that you could act upon because you just have this maze or a haze of, error bars. Regarding the vendors, I agree that's a huge issue. It's understandable, right? I mean, to dispatch and unit commit a system of 500 generators, at the end of the day, there's going to be a lot of heuristics built in, your best practices, and they're not going to give that away because they got to solve the models quickly. NREL has done a good job of making not just resource adequacy models, as you know, open source, but capacity expansion. And there the argument has been, these transitions are going to be so expensive. How do we know we're going to get there? And can we really depend on your local ISO to be candid about their modeling or their consultant? So I think that's a good sign. And that's, I think, a generational piece where, the average undergraduate or even graduate student can run these models on their PC. And you don't need a mainframe. You don't need, 12 GE engineers to do so. Will it be enough? I don't know, to overcome that. I think it's in New Jersey has an energy master plan. They have a consultant, but the model's proprietary. And they say, well, we used it in many states. That's great, but if you can't look under the hood, and I would argue, and then I'll stop. The resource adequacy models are incredibly sensitive. Maybe a year ago, I heard a presentation of PJM, several of the ISOs, I forget which ones, but 2 different ISOs were going through the very different detailed assumptions that go into resource adequacy models. I'll make up one of the assumptions. ISO A used 18 months of unavailability data. ISO B used 24 months. Seems like, well, to average, right? Is that a big deal? Well, small changes in availability from 0.8 to 0.85 matter. Which severe weather, last 20 years, last 25 years, well, it matters, or could matter. And so there is a host, I wrote a paper about this kind of a island of technicality and a sea of discretion. There's a long list of assumptions that small changes individually, let alone in aggregate, maybe they cancel out, but who knows? So I think that's an area that could be of active research.
Great. Thank you so much, Frank.
Thanks. Alberto.
Excellent. Questions for Frank? Question for Frank? So Frank, I have a kind of general question. And actually, it's two questions. One, with the as we transition to a decarbonized grid, things like resource adequacy, reliability are going to be more difficult to attain. And so this will require the grid to be basically have more resources doing fewer stuff. So will that be reflected in the cost of electricity?
Yes. Yes. I mean, one way or the other. At the end of the day, retail customers pay for electricity, or the taxpayer, or both. So if you look at, let's say, the Inflation Reduction Act, now retail electricity payers and taxpayers aren't the same, but they overlap a lot. Depends on which tax policy and so forth. So yeah, there's no way around that. Now, the question is, you of course want to factor in the cost savings of less emissions, pollutants, maybe even less dependence on fossil fuels, not just greenhouse gases, but other emissions, but also importing oil, for example, or the worldwide oil market, or natural gas, as we've seen. So those are real costs that the transition is trying to reduce, but of course at the expense. And it's also a race of technology. I mean, solar and battery costs have come down dramatically. Solar's led the way, batteries kind of in timing following. But it's not unforeseeable that in 10 years, most places, houses have solar and a battery, or most or many, 20, 30%. And it's just cost effective. So that raises issues about resource adequacy, distribution rate design, should we build out the transmission system? And I think improving these models can help. But yeah, at the end of the day, those additional costs, direct costs, will be borne by ratepayers or taxpayers. But of course, the benefits, if we achieve them, will also be benefited. Those people will benefit. And that's the rub, how to do this effectively.
Okay, related to that, would it help, the consumer eventually, that if the utility had more transparency inside the customer's rooftop solar way, the customer behavior, would that help matters? In first of all, having more confidence in your resource adequacy, as well as perhaps electricity price.
Absolutely. And of course, with the technology, smart meters, smart appliances, and all those benefits of the computational and telecommunication worlds are now entering the house, or have entered the household through, Wi-Fi, cable, et cetera, cellular. And this goes to this point I didn't really emphasize: demand response towards resource adequacy, right? So system operators, at least anecdotal reports, are reluctant. You're in the control room and there's a blackout coming. How good is that demand response across 1,000 Walmarts in your service territory versus, turning on a power plant? And if you're a resource adequacy planner, do I really want to rely on 1,000? You're just like, oh my gosh. So better metering, visibility, incentives. So this goes to the policy piece. Are there and virtual power plants, and are there ways to aggregate demand response, demand side management into something that we shrink the uncertainty bar, so it starts looking like a more viable option to the resource planner, and therefore and the policy process starts shifting resources and policies towards those areas, because it's more cost effective than keeping a dirty coal plant around for resource adequacy, or extending the life of a nuclear power plant to 80 years, right? With all those risks, or which combination. So I think now that becomes this overwhelming problem, for the reason, was it Corey who brought up, the distribution size, it's just 1,000 times bigger than the bulk power. So we can't be dispatching my battery in my house or your electric vehicle in your driveway. That's too much for the system operator, but maybe through an aggregator somehow, a DSO, distribution system operator. But that definitely is pushing our current capabilities. Of course, in 5 years, maybe that's I wouldn't say solvable problem, but a manageable problem. But yeah, visibility is key.
Good. If there are no more questions, Are there any questions for Frank? Well, thank you, Frank. Just an excellent presentation. And this is so apropos. Next week's talk will be by a professor at the University of Uruguay, where they have very large penetration, 90+ percentage of renewables. And he'll be talking about transmission planning, where the high penetration of renewables. So it just fits in very interestingly. You can see what a country like Uruguay is doing in their transmission planning. Please see if you can attend the next week's talk. That will be from the speaker will be in Uruguay. So I look forward to many of you turning up at that talk. But I want to convey thanks to Frank Frank Felder, and for the very informative presentation. Thank you all.
Thank you, Rudy. Thank you, everyone.